Okay, welcome to lecture here. We'll get started in just a second. All right, so we are going to continue on speaking chapter one, actually. We're going to wrap it up, and then we're going to go into chapter two. Again, the notes should be up there on Canvas as well. All right. So a couple things here before we get started. Very shortly today, up online on Canvas, you'll be able to find the exam one review material, which will also include the homework problems so that you can use those as well. So there's a couple questions on that. Oh, that's a nice move right there. Let's hopefully find where we're at here. There we go. All right. While we get started as well, if you could just kind of type into the chat box there if any questions that you have. But first, to just do kind of like your role, if you will. Just type in here. That'd be great. I find where we left off. Okay, so that should be it, I think. All right, so let's get started. So, like I was saying, I apologize, but I haven't clicked over to move it over. But today, up online there on Canvas, you will be able to find the homework, the exam ones type of information. Okay, so we've been talking about the atom, and yesterday we talked about some really important sort of experiments that led to sort of the discovery and understanding of the model of the atom. A reminder that what you need to know is, again, those sort of big experiments, Dalton's atomic theory, so those things that we touched upon, to the detail that we talked about it, and really sort of what those experiments were, so like the gold foil experiment, the oil drop sort of experiment, and really what sort of came out of those experiments in terms of the atom and what was discovered from the atom based on those things. Obviously, you need to know the early model of the atom, which was the plum pudding model, sort of what it was. You also need to know, obviously, the current model of the atom and what it is as well. So, where protons, electrons, and neutrons are found, um, and all those sort of locations. So, any questions on that? We then also, and again, if you do have questions, feel free to type them into the chat box. We did also talk about towards the end and sort of where we finished up last time was the idea of atomic number, mass number, and isotopes. And remember that the atomic number is the number of protons that you find in an atom. Remember that the atomic number that is the definition of it, which is actually just the number of protons. It is not protons and electrons. But as we talked about, because an atom can be neutral, what that means is if you know the number of protons, you also know the number of electrons, which are negatively charged. So it will allow you to figure out both of those pieces of information. But again, as we talked about last time, really the true definition of atomic number is just the number of protons. So we also saw that you can find the atomic number on the periodic table. It is that number that comes above the symbol on the periodic table. And we also saw that every element has its own atomic number. So you can identify what element you're talking about solely by the atomic number, the number of protons that you have in an atom. Again, no two elements will have the same atomic number. The mass number is the number of protons and neutrons that you find in an atom. The mass number is not found on the periodic table. Again, as we talked about last time, sometimes people think the number that you find on the bottom underneath the symbol is the mass number, but it's not. That's actually the atomic mass, which we'll talk about in the next chapter, I think, maybe, or later chapter. But you, all those things, the atomic number, the mass number, the number of protons, electrons, and neutrons, they are all whole numbers. So they all need to be whole numbers. And again, if you look on the periodic table on those numbers that are underneath the symbol, which is the atomic mass, Pretty much none of them are whole numbers. They're all decimal type numbers. And again, that's a good key to remember, that that's not the mass number. Now, when we do write isotopes, as we see on the screen here, we do write it basically two ways. And this is a very common way that isotopes are written, where we have on the top here, as it says, the mass number. On the bottom is the atomic number that we put there on the bottom left. And that's usually, probably for this class, the majority of the way that you would write these sort of symbols in that sort of fashion: mass number top left, atomic number bottom left. Again, occasionally you will see, which is not, I won't say occasion, but it's also very common, like we talked about last time, that sometimes, people will go like this: copper 64. The 64 in this case would be the mass number. And you could find the atomic number there on the periodic table. All right, so this is the example we went through, I think. So let's take a look at the next one here. All right, so why don't you kind of go through this example here. Let's start with this one. Why don't you take a second here. We want to figure out the total number of protons, electrons. Actually, no, I just wrote it. That's the symbol. We want to write the symbol. So we'll take a look at this one first. There's the answer. So here we wanted to figure out krypton, the symbol for it with the mass number and the atomic number. And here we're given 48 neutrons. So the first thing you would want to do, again, is go to your periodic table. And you would want to, again, look at the, this way. Maybe I find it somewhere I can find it. Periodic table. Again, we want to look at the atomic number, which is on the top of the symbol. And if we did that, we would see that it is 36. And that would tell us that it has 36 protons. Because there's no charge, and as we talked about last time, the charge would be indicated in this area. And we don't see anything indicated there. So because there's nothing written, we assume that it's neutral. And that would also tell us that it does have, obviously, 36 electrons as well. And to figure out the mass number, we would take the 84 protons. The 36 protons and the 48 neutrons. I'll get that up. I'll wake up here in a second. 48 neutrons, and we'll get to 84 for our mass number. So when I let you try the next one here, hopefully. All right, I won't give the answer just yet. So why don't you write the symbol here for nitrogen that has 6 neutrons, and we'll talk about it here in just a second. Okay, so let's take a look at this one. So nitrogen symbol is N, and it's right here. And again, we would go to the periodic table, and we look on the periodic table, and what we would see is nitrogen's number 7 on the periodic table, the number that comes above it, which is the atomic number. That would also mean that obviously it has 7 protons. That number would go bottom left of the symbol. So we would put 7 here, bottom left. And now to find the mass number, we take our protons plus our neutrons. So that's 7 and 6. That's going to be a 13, which should end up on the top of the symbol on the left. And that's how we would get to our mass number. Any questions on that particular one? Then let's continue here. So once you do this one here, we want to write the symbol for iron that has a mass number of 56. We also want to figure out the number of protons, electrons, and neutrons. So take a second there and work through that. Okay, so let's take a look here. So first off, obviously, we want to start with the symbol for iron. Iron is Fe on the periodic table. We also, again, could look at our periodic table, and our iron would be 26 there. And that 26 would be the atomic number, which would again be the number of protons it would have. So that would go bottom left, as we would put it there. The mass number was actually already given to us in here in the problem, which is 56, and that would go top left. And that would be, again, our correct symbol here. Now, our protons, as I just mentioned, would be 26. Again, we're assuming that's neutral, so we would also have 26 electrons. And to find our number of neutrons here, we would take our mass number, which is 56, and we would subtract it from our atomic number, which is 26. And that should get us 30 there, if I'm not mistaken, in terms of the number of neutrons. Any question on those examples there? So obviously, you do need to be able to write the symbols, the mass number, the atomic number, figure out how many protons, electrons, and neutrons there are. Any questions on any of that? Okay, so let's talk about a question I think that came up at the very end last time, and what happens if something does have a charge. So if something does have a charge, those are things that are known as ions, and my pen, there it is. So ions are charge entities. And there's really two types of ions. There's a cation, which are positively charged, and there are anions, which are negatively charged. And for the most part, as we'll talk about and as we'll see, cations are pretty much metals, or they come from metals. Anions, pretty much in a lot of cases, will come from non-metals. Now, what happens when something gets a charge? So let's take our nitrogen here, and let's say it had a -3 charge. And again, you would see the charge actually written top right of the symbol there to indicate that it does have a charge. So let's kind of walk through the protons, electrons, and neutrons in this sort of symbol here versus our original guy, which is right here. Now, in terms of the number of protons, the atomic number here is still 7. So we are kind of locked into that number of 7. Obviously, as we talked about last time, the protons are the most important thing. If you change the protons, you change what element you're talking about. So obviously the protons can't change. So the neutrons here as well is going to be the same in this situation because we have 13 for our mass number. We have 7 for our atomic number. So if we subtract that, that is still going to give us our, we got there, 6 neutrons. So as you can see, really the only element that is or particle that is left is the electrons. So the electrons are really what changes when something gets a charge. So overall charge here, right, is -3. So we already have 7 positives from our protons. So in order to get to -3, we actually need 10 electrons. 10 negatives plus 7 positives leaves us a overall -3 charge, and that is where the actual charge comes from. So in this case, the nitrogen, which is the nitrite ion, is an anion. Nitrogen is a nonmetal, and it has a -3 charge. Again, the number of electrons change. And that's really what happens here. If we look at our anion here, from the original that had no charge to the one with a charge, the original had 7 electrons with no charge. With a -3 charge, it actually has 10 electrons. So that is how anions are formed. They gain electrons. So when something gains electrons, they have more electrons, so more negatives than positives. So they end up with an overall negative charge. And we could also see here that the actual number of the charge is how many electrons that it gained. So it gained 3 electrons. The negative indicates that they are gaining the electrons and becoming more negative, and it's an anion. So why don't you try this one here, or these couple here, and see what you come up with. So let's do the same iron, but let's give the iron a +3 charge. And while you're at it, why don't you do oxygen with a -2 charge as well. So figure out the number of protons, electrons, and neutrons in each of those guys. In just case you don't have a periodic table, I'll give you that one, and we'll do 7, and we'll do 18 up on top. All right, so take a moment or two for each of those, figure out the protons, electrons, and neutrons in each of them. Okay, so let's take a look. We'll start with the iron here on the right. And again, same ideas before, because the atomic number, obviously, because it's still iron, is 26. That's going to tell us that we do have 26 protons. In terms of neutrons, still going to be the same here. So we're going to take our 56 minus 26. So again, in this case, it's going to give us still the 30 in terms of that. So now, though, we do have 26 positives from our protons. Overall, in this case, we're looking for, again, a +3 charge in this case. So the number of electrons here is going to actually be 23 negatives. 26 positives and 23 negatives leave you that +3 overall. And again, that is where the charge comes from. So you can see here, although the charge is the same in terms of the number, there are 3 in the first one we did, 3 in the second one we did, but here the plus is important because the plus indicates, if we look at it, our guy with the charge has now lost 3 electrons from where it started. The guy with no charge here is 26 electrons. The one with the +3 charge is 23 electrons. So the number again tells us how many electrons, but here the plus tells us that we actually lost electrons. And that would be a cation, and it is made by losing electrons. So when something loses electrons, again, they have more protons or more positive charges than they do negatives, and they end up with a positive charge. We come down here to our oxygen. Again, if we looked on the periodic table there, oxygen is number 8, and that means that it has number of protons would be 8. In this particular case here, it has a -2 charge. So overall, we're looking for a -2 charge, which means the number of electrons here, again, is going to be 10 electrons. 10 negatives plus 8 positives leaves us a -2 left over. And our number of neutrons would be 18 minus 8, which would be 10 in this particular case. So again, here the O2 minus is a anion. It gained electrons. If you had a neutral oxygen, it would have 8 electrons and 8 protons. And again, here it has a -2 charge. So it goes from 8 electrons to 10 electrons because, again, it's 2 and a minus as well. Any questions on things with charges or ions with charges, how to figure out protons, electrons, and neutrons? You do need to be able to do that as well. So if something does have a charge, you do need to be able to figure out, obviously, the protons, electrons, and neutrons. The good news is it's really just the electrons that change. So something negative charge, you add electrons. Really, you add electrons to the atomic number, it will get you, and you add the same number as the charge. So what we see here, the atomic number of oxygen is 8, and we had a -2 charge, so we add 2 to 8 gives us 10, and the minus means that we should add those, so that's why we added. And that's opposite here, what we see with our positive guy. Basically, you take the atomic number, you subtract the charge when it's positive. So our iron with the +3, iron had 26 for its atomic number. You get rid of the 3, you're down to 23 electrons in that particular case. Any questions on any of that? Okay. Just move some stuff around here. All right, so we're just going to talk just very briefly about energy. And again, as I mentioned before, we really don't cover energy anymore in this class. We used to, and they moved it out a lot of years ago. So again, when you go to 200B, you will learn more about energy, obviously like that. Speaking of 200B, let me just make an announcement. I think I got an email. I'm trying to remember off the top of my head if it's correct or not. But if you are planning on taking 200B, my understanding, I think I got an email that says you could go register now for the fall for those classes. I think they had some openings and stuff like that. The computer should let you do it. It'll assume, I think, that you'll be passing this class and stuff like that. So if you kind of want to maybe get into 200B for, I think, the fall, I think they have some openings and stuff like that. And I think I got an email that said you guys could kind of go register now for it, before they fill up and stuff like that. So just keep that in mind. If you're planning on taking 200B maybe in the fall, I think I got an email that said something like that, you guys should probably go try to add it now because they do fill up pretty quickly. And I think some in the email has said that they'll let you do that because they'll assume that you're going to be passing this class and stuff like that. So just keep that in mind for next semester. All right. Energy, again, is the ability to do work or produce heat. Work is some type of force that's acting on it. When we talk about heat and energy, heat does flow really from the warmer object to the colder. And so something that's warmer will cool down. Something that's cooler will gain that heat and energy and sort of warm up. And if they're sort of in an isolated or insulated sort of container, they'll meet somewhere in between their temperatures in terms of that. And as we talked a little bit about some of these laws, the law of conservation of energy is an important one. Energy can be converted from one form to the next, but we don't lose or create any energy along the way. And I think we might have talked a little bit about some of this, a little bit about energy, but just to review 2 important sort of concepts of energy that we come across a lot, and that's exothermic, which means that something, the heat and energy is released, and endothermic, which means that heat and energy is absorbed. And again, we don't get into too much about energy in here, but two kind of common ways that energy is sort of displayed in the calculations, for example, is Q, which if you took the pre-class, that's like what you use for specific heat, for example, specific heat capacity in that equation. But Q is heat or energy. And delta H, which is very commonly used, which is known as the enthalpy, is sort of the heat of a reaction. So when we do calculate either of these things, if we calculate Q for an exothermic reaction, it usually is a negative number, and that negative indicates exothermic. And delta H as well, when you calculate it, is usually a negative number. So sometimes if you see a delta H, and we may see that throughout this semester as well in certain chapters, because in the book they assume that you hit the energy chapter when you take this class, although we don't do that here. We will see delta H probably pop up a little bit along the way. And again, if you see it, for our purposes in this class, it really you just need to look at the sign. So if it's negative, it indicates an exothermic reaction, which means heat and energy is being released. If you see a delta H and it's positive, it means it's an endothermic reaction, and overall energy is being absorbed in that reaction. Also, Q would be a positive number as well for an endothermic. So we oftentimes will sort of represent heat, and most of the time in sort of this class or general chemistry type class, the enthalpy or delta H is used to indicate that. And again, really the simple approach to it is you don't even really have to a lot of times worry about the number. It's really just the sign. So again, if you see a negative, it implies exothermic energy being released, positive being endothermic. And there's different types of energy. There's radiant energy, there's thermal energy, there's actually nuclear energy, and there's potential energy. So potential energy is the classic one, right? Based on position, things have a certain amount of energy. The classic example of like the big giant boulder on the top of the hill that's going to fall on the person below it. It has a certain amount of stored energy based on its position. And energy can be transformed. So if that rock sort of goes over the hill, it's going to be transformed into kinetic energy. And as it starts to move, right, it's going to give off that kinetic energy as it's moving until perhaps it splatters on the ground. Once it hits the ground, it's going to actually transfer that energy right to the ground as well. And it will come to rest at a new potential energy as it fell from the top of the hill to the sort of the bottom of the hill as well. And a lot of the things about energy has to do with that. We transfer energy. So because there's that conservation of energy, if somebody loses a certain amount of energy, somebody else will gain the same amount of energy. So for example, if a reaction gives off 20 joules of energy, the surrounding air and everything around it will gain 20 joules of energy. So there's that sort of perfect transfer, we usually think about it, of energy. There's also energy, for example, stored in bonds, which is some energy we'll talk about probably in this semester when we make a bond and when we break a bond. So for example, when we break a bond, it's actually endothermic. So if you have a bond that are together, you have to put energy in there. When energy goes in, it starts to wiggle around and they get enough energy to break apart from each other. While when we want to kind of make a bond, everybody's separate from each other, they're wiggling around and all those good things. So when they lose energy, they kind of slow down, and exothermic wise, getting rid of that energy, they're able to kind of come together to make that bond. So making of bonds is an exothermic type process, while breaking bonds is an endothermic type process. Here's a couple of ways that we could sort of calculate kinetic energy, and we're not going to really do any calculations involving kinetic energy, but I will point you to sort of this relationship that we see here on the bottom. And joules is a very common sort of unit of energy, or kilojoules is another very common unit. Lowercase c, calories, is a common unit of energy as well. But a relationship that we will see is a joule is equal to a kilogram meter squared second squared. So there is this relationship here that's important. We'll actually see it, I think maybe in the next chapter, we'll kind of see that kind of conversion. And it helps us for our sort of purposes. It allows you to get everybody in the right unit sometimes. So we will sort of swap out joules and some calculations and replace it with those guys as well. All right. And like I said, here are those common sort of units of energy. A calorie, which is a lowercase c, is basically the amount of energy that's needed to raise 1 gram of water by 1 degree Celsius. And that's not to be confused with capital C calories, which is here, which we typically associate with foods. A capital calorie is basically equal to 1 kilocalorie, and that's 1,000 of the little guys there, right? And that's basically what we, nutritional sort of calories is sometimes referred to as a unit of energy. Like on treadmills and stuff like that, they'll sometimes show you maybe not the calories you're burning, but they'll sometimes show you the kilocalories you're burning. And again, that's the same thing. Basically, a kilocalorie is the same as a nutritional calorie. All right. I think we talked, that is it for that. So that is chapter 1. Any questions on chapter 1 there? Okay. We're going to go off to chapter 2 now, if I can find it. There it is, I think. Perfect. So let's do that. Hit the right button, give it a go. Maybe start at the beginning would be good. Let's try that now. All right. Let's try it here. Take number 3. Give the old college try, right? There we go. All right. That looks better, I think. Let's see here. All right. So chapter 2 is about atomic structure and really the periodic table. So we will talk about, obviously, the periodic table, as I mentioned. We are going to talk about really electrons and where electrons are in the atom, what happens to them in terms of energy as well. And I got 1 second here. There you go. That should keep that there. Perfect. All right. Go that way. Sorry, this is where like a giant screen would come in handy. I got like 30,000 boxes on my screen. Here we go. All right. So we're going to talk about electron configuration. We're going to also talk about things like quantum numbers as well, orbitals, where they are, orbital diagrams, and also, like I said, the periodic table. So a lot of this chapter will obviously focus in on electrons and what's happening there. So fireworks, for example, happens because, again, there's some different elements, as we talked about a little bit yesterday in lab. When these elements, basically, when those fireworks explode, those elements basically gain all that energy. And really what ends up happening is all the electrons in those atoms basically get excited from a lower state of energy to a higher state of energy. And that's important because everybody pretty much wants to be in a sort of lower state of energy, the sort of more stable set for everybody to be in. So as these electrons essentially will transition down from a higher state of energy to a lower state of energy, what will happen is they have to give off that energy. And it goes back to that sort of conservation of energy that we were just talking about. We don't lose energy or anything like that along the way. So in order for them to kind of transfer back down, they have to give off that energy. And if that energy basically comes off in the form of a light and a photon that has a specific wavelength, and if that wavelength falls in sort of the visible part of the spectrum where we do see colors like that red, orange, yellow, blue, violet, obviously we will see those type of colors. So depending on the elements that are present in these fireworks and the electrons transitions that they typically have, we'll see those colors. So very much like when you did the flame test, when you popped in, say, sodium, it gave off a certain color. If you did like the barium, for example, it gave off a certain color. So there's sort of known colors, if you will, for elements. So that's how they could kind of predict, obviously, what colors that we would typically see. We usually will see this kind of very simple aspect of it if you ever sort of boiled water, for example, to make pasta or something like that on the stove, and perhaps maybe it's overboiled that something was cooking. when that sort of water hits the flame that's underneath it, provided you don't have electric, but if you have gas sort of flame underneath your water that's boiling, when it hits it, sometimes you'll see obviously the flame change color really quick, almost like a yellow flame and stuff like that. And that's from the salt that's obviously in your water and stuff like that. So when it hits the flame, it excites it. You see those colors that happens. And then you go, oh, shoot, I have a big mess to basically clean up, right? So let's come back here. So when we do get colors, as I just mentioned, really from those electrons that are transitioning. And really the differences that we see sort of in those colors has to do with how many electrons certain elements have, where they sort of transition, what energy level those electrons sort of started at to what energy levels they're going to kind of finish at when they gain that energy and those transitions that we'll see. So that brings us to sort of an electromagnetic radiation here. Let's come back. There we go. And basically energy is sort of transferred through space in the form of waves. And a wave, right, is basically, you know, this sort of thing. So as it's traveling, obviously it's traveling with energy. There's some important aspects of it: wavelength, frequency, and speed. So usually kind of from the peak to peak, or the crest to crest, if you will, is the wavelength, which is abbreviated with the lambda. The frequency is basically, you know, how fast it passes a point kind of per second. So when we talk about frequency, sometimes it's very high in frequency. And sometimes it's a little bit longer, right? It takes longer for that wave to basically come. And the speed at which a wave is traveling, a lot of times, you know, the wavelength is in meters. The frequency is a lot of times in reciprocal seconds. And by the way, a reciprocal second is the same as a hertz, which is another very common unit of frequency. And frequency is sometimes abbreviated with the little, although people call it a V, is really new. It's that sort of symbol there. And a lot of times the speed of a wave that we sort of look at is a lot of times in meters per second, right? So that sort of makes sense in terms of that. And you know, waves, obviously they do carry a certain amount of energy. So if you've ever been obviously to the beach or anything like that and in the water and you get hit by a wave, you know there's a lot of energy happening there, depending on how big the wave is, right? So it will sort of can move you very far if you sort of get hit by that wave. So let's take a look at some of these characteristics, although the symbols miss the boxes there. So I'll just fill them in again. That's the wavelength there. It's hidden right there. And there's our frequency symbol, which is our new, which is our frequency. So the wavelength, as I mentioned, is really that distance between kind of two peaks or two troughs in a wave. And a lot of times it is basically given in meters. Frequency, as I mentioned, reciprocal seconds is a very common unit of it, 1/seconds. Or again, a hertz is a very common relationship that we use for frequency. So again, a reminder, a hertz is the same as a reciprocal seconds. Now, c is the speed of light. That's a constant. And yeah, good question. I personally don't use this number either. It seems like a lot of digits. I personally use the 3 × 10⁸ meters per second. So that's perfectly fine. You could use that number. I personally use the 3 × 10⁸ as well. Yeah. If you want to use the bigger number, you can. I don't know. Some books like to use it, and some people like to kind of use that spread out number. But I think in the end, you get probably about the same number if you just round it to 3 × 10⁸. So like I said, I'll use 3 × 10⁸ as the speed of light. Again, it's a constant, not always given to you directly, but it's assumed that you know that that's a constant and that you do have that value available to you. So there is an important relationship between those guys, and let me actually give you that relationship. I think it went somewhere. If we take the c, which is the speed of light, equals the wavelength times the frequency. So that's an important calculation or formula. So make sure that you have that there. And again, if we put in our units of wavelength is meters, our frequency is basically 1/seconds. So again, when we get to our speed of light, that's where we get our meters per second from. We also can use this to rearrange. So if we wanted to solve for the wavelength, it would be C divided by the frequency. And again, in terms of units, meters per second would be on top. The frequency would be 1 over seconds, which means essentially the seconds would cancel and we would end up with meters in terms of the units. So that's another important rearrangement of that equation. And lastly, frequency would be basically the same deal. Frequency would be C divided by the wavelength. And here, C is again going to be our meters per second. Wavelength going to be meters. Meters will cancel, giving us reciprocal seconds as the frequency. So really, again, this equation here, a formula you do need to know, and a reminder that formulas will not be provided for you on exams. You do need to know them, but constants or anything like that would be provided for you. So something like, C is 3 times 10 to the 8 would be provided. But again, the formula here will not be provided. So you do need to know those formulas. So that one's a good one to know. Again, how to rearrange it allows you to sort of obviously solve for any of those three things, the wavelength or the frequency, obviously the speed of light you're given. Any questions on that? All right. So now that we actually have the formula here, let's try an example here. Why don't you give it a go? Calculate the wavelength of red light with a frequency of 4.62 times 10 to the 14. So why don't you take a second or two and give that a go, and then we'll talk about it. And if you want, you could calculate it in nanometers. It doesn't say to, but why don't you calculate it in nanometers? And here's the conversion for nanometers if you need. Okay, so let's take a look and see how we're doing. So here we're given the frequency, and we want to calculate the wavelength here in nanometers. And some stuff here. All right, so we would want to use our equation. Our C is equal to our wavelength times our frequency. Here we would want to solve for wavelength, which would be C divided by the frequency. So in this case, again, C is 3 times 10 to the 8 meters per second, which is our speed of light, divided by our frequency, which is 4.62 times 10 to the 14 reciprocal seconds. This brings up a good point just to remind everybody, when you do have numbers in scientific notation, you want to make sure that you are using your exponent button, which on your calculator looks something like these buttons. Some newer calculators may even have a button that's like times 10 to the n or something like that. But if you have these two buttons, when you do push something like 3 times 10 to the 8 in, you would hit 3, you would hit that exponent button, and usually it'll do the 3 and an E, or it'll pop a 3 and some zeros up or something like that. And then you would just hit 8, and it will look something like this when you do that. If it's a negative exponent, you would do kind of the same thing. Hit the 3, hit your exponent button, hit the negative button, which, by the way, looks something like this. So negative button like that, or like that usually. Do not hit the subtract button. And then you would hit 8, and again, 3e minus 8, or 3 minus 8, something like that. That E stands for the times 10 part of the number, so you don't have to hit the multiplication button. You shouldn't hit any of those things. By the way, you shouldn't be using the inverse log or anything like that to actually punch it in scientific notation. You definitely want to make sure that you are using your exponent button. You can find out really quickly if you're not using your exponent button correctly, because pretty much all your answers will be off. The front number will look really good, but the exponent part will be off when you punch it in. So make sure that you do use your exponent button when you are doing that. So again, if you punch that in, you got 3 exponent button 8 divided by 4.62 exponent button 14. And you get this number here with a lot of zeros. And that would be 6.49 times 10 to the minus 7. The units here would be meters, as the seconds would cancel. Now, since we're going for nanometers in this particular case, which is a common conversion, this is our conversion, and very common people always kind of do this conversion backwards. They always think it's 10 to the minus 9 nanometers in a meter. So when you see that on like a little chart, so if you went to the chart, it would say like nano is 10 to the minus 9. And what that means when you go to that sort of chart is that's how much there are in the base unit to one of the prefix units. So the base unit in this case is meters. The prefix unit is nanometers. So 1 nanometer would be 10 to the minus 9. I can't tell you how often people get those backwards. They always want to reverse it the wrong way. So again, here, if we set it up with some dimensional analysis, so everything cancels out in terms of units, we would have 10 to the minus 9 meters on the bottom, 1 nanometer on top. Meters would cancel, so we're going to divide by 10 to the minus 9, and that's going to give us 649 nanometers, which is about where we would expect sort of red light to come in. Red light, which is a visible light, is around in the 700-ish region, so that is good. Any question on that calculation there? By the way, if you do have a newer sort of calculator that does have, in fact, this button here, I'm sorry, no, I'm just kidding. I think they're oftentimes kind of multicolored, kind of like a blue, green, blue, blue, white, green, blue. I see those colors, right? Green, white, and blue, green. Never mind. Green and white and blue and white. There we go. I got it right. All right. What you typically have to do on those calculators, because of the way they're programmed, and they're kind of the newer ones as well, they're not programmed really well. So if you don't put parentheses around every number, it will give you the wrong math. It'll do the wrong math. So if you had to, one of those newer calculators, and you're still having trouble, what you need to do when you enter it is actually put parentheses around this number, parentheses around the next number that has a sort of scientific notation in it. Otherwise, it really will do kind of like the weird math or something like that. And it's just really the way it's programmed. Any questions on that calculation there? Technically, you're not really allowed to use graphing calculators. You just should use a basic calculator and stuff like that. And not really nothing too programmed, yes? Okay. Other questions? All right. So why don't you try this one here? We have a frequency of a radio station, which is 100.7 megahertz. What is the wavelength? And this one you could do in meters if you want. So you could do this one in meters. So take a moment or two here and sort of figure it out. Okay, so let's take a look. So we want to kind of use the same formula here. So our C is equal to our wavelength times our frequency. Here again, we're given the frequency and we're looking for the wavelength. So we are going to solve for our wavelength. Remember though that the speed of light is in meters per second. And here though, we are given units of megahertz. And megahertz is like when you listen to the radio station is 101 megahertz, right? Which is 101 on your dial. And mega is basically 10 to the 6. So again, what that means is in 1 megahertz, there really is 10 to the 6 of the base units, which is a hertz. And also a reminder, as we saw before, a hertz is the same as a reciprocal second. So that's how they get down to basically that being a reciprocal second. So really just need to kind of plug it in. And we would take our 3 times 10 to the 8 meters per second. But again, before we do plug in our frequency, we do want to convert it. So 100.7, and I'm just going to convert it, megahertz. And we'll use our conversion that in 1 megahertz on the bottom, there's 10 to the 6 reciprocal seconds on top. Again, these guys will cancel in terms of units, and that would get you 1.007 to the 8. And these units now would be reciprocal seconds, which is what we need here. So we would put that in here. The seconds are going to cancel here. That's going to leave us with just meters, which is good. Again, we want to make sure we're using our exponent button. So 3 exponent button, just 8, divided by 1.007 exponent button and 8 as well, gets us 2.98, looks like. And the units here are meters in terms of the wavelength. So radio waves, which is where this is on the electromagnetic spectrum, which we'll see in just a second, is in a different area than the previous question, which is visible part of the spectrum where we can see color. So the question is, do you have to use scientific notation for your answers? The answer is really no, unless it specifically asks you to give the answer in scientific notation. More importantly, you do need to give the answer sort of to the correct number of significant figures and so forth. So sometimes the only way you could kind of give the answer to the right number of significant figures is to write it in scientific notation, but you don't have to write it in scientific notation if you don't want to, unless, again, it specifically asks you to do so. I keep drawing big lines across the screen. So yeah, let me explain that and try not to draw any. Whoops. There we go. All right, so let me try this. Let me try to get rid of some of the, there we go, crazy lines that it drew. All right. So the question was, how did we get to the 1.007 times 10 to the 8? Okay, so it was down here on this conversion down here, and so it is from this relationship here. Really, I'll do it right here. That mega is 10 to the 6. So this is megahertz. So we want to use that conversion really to go to hertz, which is this conversion here. So mega, which is 10 to the 6, means in the base unit, which is hertz, there's 10 to the 6 hertz and a megahertz. And that's what this conversion was that we did. We basically took 100.7 megahertz. And because mega is 10 to the 6th and 1 megahertz, there would be 10 to the 6 hertz. So these guys cancel because when you divide megahertz by megahertz, they cancel out to 1. It's like when you divide 2 by 2, it equals 1. So the units also cancel out like that as well. So basically we take 100.7 and we times it by essentially 1 times 10 to the 6. So on your calculator, you could take basically 100.7, you could multiply it, and you can probably just go 1 exponent button 6, and it should get you to this number here. And again, a hertz in this case is the same as a reciprocal second, so that's why it comes out that way. Any questions on that? In terms of rounding, I'll put it this way. In terms of rounding for these type of problems, a lot of times they will kind of give you an idea as to where they want the answer to. So, for example, the lab I think that we're going to do today, they'll say like take it to 2 decimal places or something like that. So probably follow the instructions that are there. If not, then you can probably go by the number. The reason we went to really 4 here is because this number has 4 significant figures. So when we wrote it over here, we also had 4 significant figures, so we didn't lose any significant figures here. But in terms of answers, sometimes they will give you sort of where to take it to on sort of some of these problems and stuff like that. Other questions? Okay. So obviously you do need to be able to calculate the wavelength, the frequency, given that particular pieces of information. Okay. So let's talk a little bit about waves that we have before. And there is a relationship really between waves and energy. And when we have a wave that has a longer wavelength, it typically will have a shorter frequency. And usually what that relates to is a lower energy. And vice versa, if we have something that has a smaller wavelength, it usually will have a very higher frequency. And usually in terms of energy, it will have a higher energy. So we just look at sort of these waves from different colors of light. So that's the red, that's green, and obviously that's in the bluish range. We see that the red wavelength here is much longer than the green, and obviously much longer than the wavelength that we see for the blue. And we also see that the frequency is sort of spread out more in the red versus the green where it happens, and it goes really crazy here in the blue sort of section. And what that basically means is in terms of energy, this guy here, the red color of light, is actually lower in energy than, say, our blue color over here. This guy would be higher in energy. So by looking at the wavelength and the frequency, you can kind of determine sort of energy. And these energy that's given off a lot of times will be given in the form of these waves, and they may fall in this part of the spectrum, which is the visible part of the spectrum, but they may also fall in other parts of the spectrum, which we'll see here in just a second. So let's take a look at that. And to answer your question, it will probably be a little bit of both. So there'll be some multiple choice part, and then there will be probably a free response part in terms of the exams. So this is what is known as the electromagnetic spectrum. And you do need to kind of know the electromagnetic spectrum. And what I mean by knowing it is you don't necessarily need to know exactly where everybody breaks off at, but you do need to know in terms of sort of energy, if you will, almost like the pre-lab sort of questions that are in the first couple. You need to be able to put things in order based on sort of higher energy, lower energy, longer wavelength, shorter wavelength. So up on top here is our wavelength in meters, and on this end we have 10 to the 4, and on the other end we have 10 to the minus 12, and this end is a smaller wavelength. On this end is a longer wavelength. So as we just talked about, what that should mean in terms of energy is on this side over here, where we have our smaller wavelength, is going to be higher in energy. And on this end, it's going to be lower in energy. Right? Now, we do see things like radio waves. Obviously, like when you're listening to the radio in the car and all that, that is where that comes off of. Sorry, just trying to move some stuff out of the way here so I can see. Over here we have radio waves, and at the shorter, sort of a longer wavelength, lower in energy, that's not too dangerous. As we sort of progressively go this way, the wavelength gets shorter and there's more energy. Then we have microwaves. So that has enough energy, right, to move your water molecules really fast in your food and heat it up. We have infrared is typically where we kind of feel heat. This is the visible part of the spectrum. This is where we see colors, right? That's our Roy G. Biv, right? And we also see in colors, as we just saw with that previous slide, there is a difference in energy. Red being a longer wavelength is lower in energy than our kind of purple color over here, which is shorter in wavelength and higher in energy. So again, if that energy is coming off in the form of a wave and it falls in a wavelength in this area of the spectrum, that's why we see colors. So that's why we see the different colors that we do see. Ultraviolet, UV, a little higher in energy, right? Which is why we put sunblock on, right, when we go outside so we don't get too burnt. X-rays also very high in energy. Why? When they give you an X-ray, they give you like a lead vest. They walk out of the room. They don't stay in the room with you. And also gamma rays, as we talked about earlier last time, is really just pure energy and so forth. So as you go from right to left there, you get higher in energy, lower in wavelength, and or shorter in wavelength. As you go the opposite way, you're going lower in energy and longer in wavelength. So you do need to know the order here on the electromagnetic spectrum. You do need to know, like I mentioned, the order in terms of energy, putting things in order in terms of energy, putting things in order in terms of wavelength. And that includes also the colors down here in the visible part of the spectrum. You do need to know. The visible part of the spectrum is oftentimes given in nanometers. So usually if you're sort of figuring out the wavelength here in the visible part of the spectrum, a lot of times we do just sort of give the answer in nanometers like we did on that question that involved the red wavelength. Any questions on that there? So again, you do need to know this. You don't need to know exactly the numbers where it breaks off, but you do need to know the order. That's a pickle. Good talk. So when we talk about electrons sort of moving from one energy level to the next, oftentimes we hear this word known as quanta of energy. And basically what this idea is, it's you don't have to worry about the pickle. It's just to show that energy is basically happening in that reaction. Don't worry about the pickle. I probably should have took it out. I just haven't taken it out, but you don't have to worry about it. So the energy of an electron as it transitions from one energy level to the next. So for example, if this is our energy level here, and we have an electron here, and it wants to go to this energy level, it will gain enough energy basically to make it to that energy level. And that energy is basically represented by, all these guys are in the wrong spots over here, by H times the frequency. And what that essentially means is it will gain enough energy to get to that energy level, and vice versa. If it started up here on top and it wanted to come back down, it would gain enough energy to do that. And that's what's known as a quanta of energy. And basically what that means is it's kind of like when you walk stairs. When you walk stairs, you don't go like halfway from one step to the next and go, I'm kind of tired, I'm going to take a rest in between. Usually most people have enough energy to go from one step to the next, up or down. And it's sort of the same way how electrons travel. They gain or lose enough energy to go from one energy level to the next. And that is sometimes what is referred to as a quanta of energy, or these sort of packets of energy that they either gain or release. And it's represented by this equation, which you do need to know. E equals H times the frequency. E is energy. H is a constant, and that's what's known as Planck's constant. And we'll see it, but it is 6.63 times 10 to the minus 34 joules times seconds. So 6.63 times 10 to the minus 34 joule seconds. That is a constant that you always have, like the speed of light. And nu is our frequency like we saw before, which is in usually reciprocal seconds. So if we just look at this formula here, joules times seconds and times reciprocal seconds, those seconds will cancel. And when we calculate the energy, it is typically in the units of joules when we use this equation. So that one, along with our good friend that we saw earlier, are two important equations, because as we saw before, if you put them together, the frequency is equal to c divided by the wavelength. And since E is equal to h times the frequency, you actually can substitute it in, and you get this sort of version of the energy equation, which is also an important one to remember. The energy is equal to h times c divided by the wavelength, and h and c are both constant. So h is our Planck's constant, c is our speed of light, which means, again, if you just know the wavelength, you could figure out the energy that's associated with the wavelength. And obviously, if you just know the frequency, you could use this guy up here. So knowing the frequency alone could allow you to figure out the energy. If you know the wavelength, you could use this sort of version of it, and you'll be able to figure out the wavelength from the energy from just the wavelength. So those are two really sort of important equations and how they tie to the previous one that we saw. Any questions on that? All right. So I jumped a slide. Let's come back. There. So again, we could use that to calculate the energy of a photon. So basically, as we've been talking about, as we have these electrons from these different energy levels, as they go up and as they kind of come down, when they give off that energy as they come down, that energy of that wave that's coming off is equal to E times H times the frequency. And again, that's going to come off really as a wave of light that has energy associated with it. And that's what is sometimes referred to again as a photon of light. And they did a lot of experiments, especially Einstein and so forth. And Einstein has a formula there, which is E equals mc squared. And it gives us that dual nature of light. So a lot of things that we're talking about here, which are particles. Electrons are obviously particles. There was a lot of experimentation done by Einstein and others that basically decided that both particles have wave functions. So particles, although they are particles, they do have some properties that are very similar to waves. And they can, in certain situations, behave like waves and have wave-like function. And I'm not sure if I lost the screen there. Let's just make sure it's still going here. There we go. All right. So electrons, which are particles, do behave like waves, and waves do have some particle-type properties. So this is what's meant by sort of the dual nature. There's sort of both particles and waves basically have properties that are very similar to each other. This is Einstein's equation here, which is E is energy, m is mass, right? And this is our speed of light, right? We don't really do too much with Einstein's equation here, but it does help explain the idea of energy. He did an experiment was known as the photoelectric effect, where he saw that electrons would bounce off a surface of metals when irradiated with a certain amount of energy given off in terms of light, and you're able to kind of eject electrons from it. So as these electrons are sort of transitioning from one energy level up and down, and mainly down, they will typically give off a certain type of spectrum. And there's two types of spectrums. One is a continuous spectrum, when we see really light throughout all of the wavelengths coming out at once. And so if we pass sort of white light through a prism, and a prism basically will, as the light comes in, kind of separate out the light into different colors. There, I'll look red on the screen, but imagine some different colors there. And we'll typically get this sort of continuous spectrum. So sometimes a continuous spectrum is thought of almost like a, almost like a treadmill, if you will, or a hill. Right? You pretty much can step anywhere you like along the way. Right? So if you're walking up this hill, for example, you could step here, you could step there, you could step there, you could step anywhere you like along the way, because pretty much energy from all the wavelengths are pretty much getting given off at once. Now, elements in their gas state, for example, and heated solids will typically give off a spectrum which is known as a line spectrum. And in a line spectrum, what we see is distinct lines occurring at distinct wavelengths that correspond to electrons transferring from one energy level to the next. So what that means is electrons, as we mentioned, have enough energy to make it up to this energy level, have enough energy to come back down to this energy level. And again, that is that E equals H times the frequency. And when they do that, what they do is they give off these distinct lines in terms of their spectrum. And again, they come out at specific wavelengths. They come out with specific colors in the visible part of the spectrum when you're able to see that. So this is that quantized version of energy as they're kind of doing these transitions. And it's, again, sort of related to like stairs. So sort of this quantized level. Again, when you're walking upstairs, you have enough energy to get to here. Or if you're not on that step, you're probably going to be on this step. If you're not on that step, you're going to be on this step. And that's different than sort of a continuous spectrum where, as you can see, you pretty much can stop anywhere along the way as you're going. But here you've got to be pretty much at distinct levels. You got to be at this energy level, for example, that stair, that energy level, that energy level. Again, you don't typically find yourself kind of between two different sort of stairs or anything like that, or energy levels. Now, hydrogen, for example, will give off an emission spectrum. Emission spectrum is a result of those electrons coming back down in energy, like we see here. And when that wavelength comes off, it's going to emit a photon. And that's why it's called an emission spectrum, where we see the colors that are coming off as those electrons are transitioning downward. So the significance of only certain energy levels being allowed in electrons and hydrogen is, again, this idea of quantized energy, which they do need to gain or lose a certain amount of energy to make those transitions of those electrons going from one energy level to the next. So why is it significant that color emitted from hydrogen spectrum is not white or white light? And how does the emission spectrum support quantized energy? So if levels were not quantized, so if these electrons, as they're transitioning from one electron to the next, one energy level to the next, if they were not quantized, what we would see is white light, for example. White light is basically means that we see white light because all the colors basically are released at one, all the energy is released at the same time, which means all the colors are emitted at once. So we see basically just kind of white light. Now, when we see something like hydrogen, for example, we see distinct colors. So when you look at the hydrogen spectrum, which you might today as well, you will see these distinct colors occurring at these distinct wavelength and this more line structure. And again, what that means is we have these quantized energy because, again, one of these lines may correspond to, for example, this line here may correspond to the electron starting up here and coming down to this energy level. While, say, this line over here may be this electron here coming all the way down to, say, this energy level down here as it gives off that energy. So because we see these distinct lines, what that represents is that these electrons are transferring from one energy level to the next in a whole number of packets of energy, and they're not stopping anywhere along the way. So again, if they were sort of stopping along the way as they were transferring, like they could stop here, they could stop here, they could stop here, they could stop here, we would see all these wavelengths coming off at once, and we would see sort of white light happen. And since we don't see that, what we know is we have only really a distinct transition occurring, say, from here to here. And it's only going to give off this one wavelength of energy as a result of that transition. So again, we know it's not a continuous spectrum, because otherwise we would see a ton of different colors coming off all at once. Any questions on that there? So electrons in the hydrogen atom move around an orbit, and this is what Bohr's model of the atom was. Bohr's model of the atom was more of a planetary model, where he thought the nucleus, come here, maybe, there you go, the nucleus here, and basically he had these orbits around the nucleus, very badly drawn, where these electrons could travel in these kind of circular patterns. This would be like n equals 1, n equals 2, n equals 3. N is the principal quantum number. And it is basically the energy level. And n equals 1 is the ground state. And anything above n equals 1, n equals 2, 3, 4, 5, 6, 7. These are what are referred to as excited states. The ground state is the lowest in energy. The excited states are the higher in energy, or higher in energy states. So Bohr's model is not correct very well, or doesn't work really well for everybody outside of hydrogen, but it does work really well for explaining sort of the lines that we do see in hydrogen. So in hydrogen, again, the lines he thought was associated with an electron from this orbit transferring down, say, to that orbit over there. Again, it's going to give off a certain amount of energy in the form of light to do so. Well, again, if you had an electron over here transitioning down to here, it would give off a different wavelength of light. And that's what we see here. Again, in terms of the transitions, for example, this electron here going from the 5th energy level to the 2nd would give off perhaps a blue color of light, while this guy going from the 4th energy level to the 2nd would give off a green light. This guy going from the 3rd energy level to the 2nd would give off like a red light. We could also look at this and relate it to what we were talking about in terms of wavelength and energy. We would see here that blue went from the 5th energy level to like the 2nd. That is like 3 energy level switch. That's much more energy, right, than this required than, say, this transition here, where it went from n equals 3 to n equals 2, which is only like a 1 level change. So you can see it has we would predict that red here would have a would have a longer wavelength and a lower energy. While here we would predict, because that's more energy to do those transitions, go from that many energy levels, we would predict that blue here would have a higher energy and by default would have a smaller wavelength in that case. Any questions on that? So when we see these distinct line spectrums occur, we know that we do have electrons transferring again, and sort of like the stair situation, going from one step to the next, again, not stopping anywhere along the way. It's either going to be found on like the first step, if you will, the third step, wherever it may be, but it will never find itself in the middle. And as I mentioned before, because we have sort of that full transition that occurs in terms of energy, we only really see one wave come off. Again, as I mentioned before, if it kind of was able to stop anywhere along the way, everywhere it would stop would give off a wavelength of light, and obviously we would see a lot of colors coming off at once, which we don't see in terms of elements in their gas phase. All right, so I'm not going to go crazily over again like I did last time. So what I'm going to do is, I think we're going to, at this point, we're going to stop here in terms of lecture for today. But what we're going to do is, I think we're going to have lab at 9:45 like normal. And what we're going to do Yeah, I'll go back to that when I'm talking here. What we're going to do, I think, is we're just going to lecture just a little bit more in lab at the beginning to cover a couple of concepts. We're not too far away, I think. The concept is that the concept check one. That's way back, I hope. I'll find it for you in a sec. But we're going to just do a little bit of lecturing at the beginning to get us to the topics that you need for the lab for today, and then we'll go off and do the lab and all that. And other than that, so I'll see everybody at 9:45, and I will go try to find your concept check here for you in just a second. All right, so you're good to go. I'll see everybody at lab at 9:45. This one, right? I think is that the one you're talking about? Okay, knew it was here somewhere. All right, I'll see everybody in about 20 minutes or so for lab. And again, we're going to do a little bit of lecturing, and then we'll get to the lab. Yeah, let's see. So the idea here is it's when we see the spectrum for hydrogen, it's a line spectrum, which again implies that we're getting only distinct energy to come off or wavelengths of light to come off. What it means is in order for that to happen, as the electron comes back down, it has to have enough energy to go completely from this energy level all the way down to this energy level here without sort of stopping, if you will. And because it kind of goes directly from one energy level all the way down to the next, is what's known as quantized energy. And that means that it will only really give off one wavelength of light that corresponds to that energy difference. And that's different than what we see up here that I drew. In a continuous sort of spectrum, what we would see is it's kind of stopping all the way along the way, our ability to stop all the way along the way from, say, one energy level to the next. And as it would kind of go through each of those energy levels, it would give off, light and energy everywhere along the way, which would all combine basically to kind of give you white light. Because white light is basically all the energy coming off at once, all the wavelengths coming off at once. And that's why they combine to make sort of that white light region and stuff like that. So we wouldn't be able to see distinct colors if it wasn't quantized energy. It would just all come off at once, and we just see sort of white light versus, a red light, a green light, or something like that. Good? Perfect. Okay. I'll see everybody in lab.